Hi, everyone, and welcome to GIA Knowledge Sessions, a series of talks and seminars about gemology fueled by our decades of research. At GIA, we consider ourselves so fortunate to study and learn from gems, and it's our mission to share our discoveries and learnings with the world. I couldn't be more excited to kick things off today. My name is Natalie Jaden. I'm the Content Marketing Manager at GIA, and I'm joined today by Dr. Evan Smith, one of our GIA research scientists. Before we get started, just a few things of housekeeping. Everyone attending this is automatically muted. If you have a question, please submit it using our Q&A feature you'll see at the bottom of the screen. Feel free to ask questions as we go. There will be a Q&A session at the end where Dr. Smith will have the opportunity to answer some of your questions. We'll also send a recording of the session to you later today, and a message will have a survey we'd love to get your feedback on. And with that, I'm going to pass it over to you, Dr. Smith.
Thank you, Natalie. So today we're talking about inclusions. And quite often when people start talking about inclusions and diamonds, they immediately think of this is the clarity scale. And inclusions have a bearing on the clarity of diamonds. And sort of the most desirable or most valuable diamonds are those at the left that don't have any inclusions at all. And these are sort of what people ogle over, like this 102 carat D flawless diamond that was sold last October. So this diamond doesn't have any inclusions in it whatsoever, but actually in its rough state, this diamond did have some inclusions. They were just cut and polished away during the manufacturing process. So this is that diamond. It's from Canada. And you can see these sort of black ragged things trapped inside the diamond. And most of what we can see here, this black material, is probably graphite. Graphite, that makes sense. Graphite is made of carbon. The diamond is made of carbon. This is one of the most common things we see trapped inside diamonds. So here's another diamond. This is a fancy blue diamond, and it's got all these black inclusions trapped inside it. So today I want to give you kind of an overview of what some of the most common inclusion materials are that we see out there in diamonds, and some of the techniques that researchers like myself might use to identify them. So inclusions like these might sort of detract from the value of diamond, but inclusions can actually be quite interesting, and they can be very beautiful sometimes. For instance, this inclusion here in a fancy light pink diamond, this is an inclusion of ferropericlase, and it's got this vivid iridescent effect with colors all over it. In my opinion, this is a very attractive inclusion that I'd be very happy to have in a diamond. So this is just one example of many different kinds of inclusions out there. So inclusions are trapped inside the diamond, and they're actually trapped while the diamond forms. So a natural question, besides what is this material, but sort of is where is this material from? And for that, we have to think about where diamonds come from. Where do diamonds come from? Well, we find them at the surface of the earth. We mine them quite often from these primary volcanic deposits. These are quite often kimberlites. And the kimberlites are a volcanic rock that have traveled upwards from great depths, from somewhere below about 200 kilometers deep. And this is where most diamonds form. So we think most diamonds come from a depth of about 150 to 200 kilometers deep in the earth. And this is, for a ballpark, maybe around about 100 miles. And the inclusions in these diamonds are actually a snapshot, a very well-preserved snapshot of what happens inside our planet. This is a depth that we can't dig down to. We can't access it in any other way. And there really aren't other minerals or rocks that come from this depth well preserved. So diamonds are a really valuable way to see what's happening down in the earth. So here's a diamond here that's growing. It's getting larger, and it might envelop some neighboring mineral grain that becomes trapped inside the diamond. So this is now an inclusion in a diamond. And the idea is that when we see diamonds at surface, they've been transported a long way, all the way up to the surface of the earth. And we can find diamonds that still have these inclusions trapped inside them. And those inclusions are really well preserved because the diamond encapsulating that material is very hard and almost chemically inert. So it's very good at protecting that material. So we sort of zoom out a little bit from this cross section. So, and sort of try to fit it into a larger geological context. Here's that cross section I just drew, and it fits about here on this cross section. So we're saying that most diamonds form in this region here, about 150 to 200 kilometers deep in the base of the oldest and thickest parts of continents. And sometimes this is referred to as the mantle keel or the lithospheric keel. And the place where diamonds form is sometimes called the diamond window. So the inclusions we see trapped in diamonds are from rocks that exist in this environment, sort of diamond host rocks. So when we actually look at inclusions in diamonds, we might see something like this. Sometimes they're brightly colored, and that can be a clue as to their identity, but there are more tools that we have at our disposal. So let's talk about how do we actually identify inclusions. So first, I would list the simplest thing here is just visual inspection. So using a loupe or better yet, a microscope so you can really get some magnification there and examine these inclusions up close. And we can observe things like the color or the texture or the luster of those minerals. And sometimes that can be helpful and we can almost make a positive identification of some mineral inclusions, but often we need some more information in order to positively identify what this inclusion is. So I've listed here some sort of three advanced approaches, and they're broken down by what they're trying to do. So the first thing is, well, you could try to identify the composition of this included material. In other words, what elements is it made up of? If we have an inclusion like this, what are these actual little atoms? And one of the techniques we could use is something like EDS on an electron microprobe, or actually trying to quantify the different proportions of these elements. So using an electron microprobe, we can identify not just which elements are present, but how much of those elements there are. Another technique we could sort of try to do is identify the crystal structure. So not just what these atoms are, but how they're arranged. What is the 3D pattern of atoms? Because minerals always have some kind of a 3D regular structure to them. And that structure can help us identify what mineral it is. And the big tool people use to do this is X-ray diffraction. And the last thing I want to mention is vibrational spectroscopy. In other words, how do the bonds in this material kind of jiggle? You can almost think of minerals as being made up of atoms that are kind of joined together by springs. They can sort of vibrate a little bit. And that vibrational sort of frequency or energy is specific to some minerals. So by learning something about how these bonds vibrate, we can say something about what the identity of this mineral is. And the two main techniques people use that rely on this sort of phenomenon of vibrational spectroscopy would be Raman spectroscopy and infrared absorption spectroscopy. A lot of what I rely on is Raman spectroscopy, and I'll show you some examples of this. So let's talk about identifying minerals based on composition. So here's a diamond here. It was an octahedron of about 3 carats, and I've polished into it. So now we can see a cross section through it, and it's got lots of inclusions in it. Under the microscope, we can see that it has these sort of glossy looking, colorless inclusions. So what are they? Well, this material, because some of these inclusions are actually exposed on this polished surface, I was able to take this sample to an electron microscope, and you can actually see it here. So this is zoomed way in. So the scale bar here is 10 microns. So the width of this image is smaller than the width of a human hair. The gray, the dark gray background, that's the diamond itself. And this lighter gray material, these are the inclusions. So there are many little inclusions exposed here. And using EDS, which is electron dispersive spectroscopy, we can see, in a sense, what elements are present here. So the idea is that you're going to bombard this little inclusion with electrons, and then the atoms in that material will give off X-rays, and the X-rays are characteristic of the different atoms that are present. So in this material here, if we do this, the EDS spectrum looks like this, and we can see this material is made up of oxygen, magnesium, and silicon. It has a little bit of iron too, but for the most part, this says that these inclusions are made up of magnesium, silicon, and oxygen. And the material we're actually looking at is olivine. And this is the chemical composition of olivine. And if we wanted to, we could take this to an electron microprobe and actually get a more quantitative sort of picture of how much magnesium, how much silicon, and how much oxygen is present. So we can work out those proportions and actually work out, and that's the sort of what this mineral formula is based on, is these proportions. How much magnesium do you have? So we can identify minerals if we know their composition, in a sense. The other piece of information that's handy to have is something about their structure. So structure, crystal structure, is the idea of, well, how are these atoms, the magnesium and the silicon, how are they actually arranged in 3D space? So here's a little cartoon of a crystal structure here. And what is characteristic of this material is the sort of spacing between these atoms and the three-dimensional geometry. Any crystal has sort of repeating, evenly spaced layers in 3D, and knowing something about the spacing and the layering and the orientation of all of those things is a way to identify the mineral. As I mentioned, the most widely used technique that sort of gets at this idea of crystal structure is X-ray diffraction. And it looks sort of like this. So we've got our crystal, our sample here, and this could be an inclusion. And we've got an X-ray beam coming in that's going to interact with this crystal or our inclusion. And because it's a crystal here, we know that inside it has these repeating, evenly spaced layers in 3D that should interact with this X-ray beam and cause a phenomenon called diffraction. So most of the X-ray beam will just pass right through this crystal, but some of these X-rays will be diffracted by the crystal itself. And when I say diffracted, I mean they'll sort of be deflected almost, as in a specific way, depending on the spacing and orientation of these crystallographic layers. So here we've got some X-ray beams that have been diffracted, and they will make a sort of pattern on this detector screen here. And the pattern might look something like this. So we've got little spots here where we see diffracted X-ray beams, and this sort of arrangement of this pattern gives us direct information about the underlying crystal structure of this material. So I've used this technique with this diamond here. So it's a small gray diamond. It's about 1 millimeter across, and I've polished a cross section through it. And you can see this is in the electron microscope again. We can see all these little tiny white dots inside this diamond. And all of these little white dots, if we zoom in on them, we can see these white dots are actually little tiny crystalline inclusions that are maybe 1 to 3 microns across. So they're very, very tiny. But I was able to identify these inclusions using X-ray diffraction. So if we pass an X-ray beam through this material and look at the pattern of diffracted X-rays from that, we see something like this. It's actually the diffraction image that I showed you a couple slides ago. This is from this diamond. And all of these spots here are giving you direct information about the crystal spacing and orientation of the inclusions. And this is sort of diffraction in 2 dimensions. We see these diffraction spots, but it's common to take this information and have it collapsed. Instead of 2 dimensions, we can portray it in 1 dimension. So instead of bright spots, we have peaks arranged, peaks in intensity arranged as a function of, this is 2 theta. So this is sort of the distance away from the middle, essentially. So this is showing us direct information about the spacing of these crystallographic layers. And this lets us see that while this sample with all those tiny, tiny inclusions, those tiny, tiny inclusions are olivine. So again, we're seeing inclusions of olivine. Okay, let's talk about vibrational spectroscopy. So here's another diamond. This is a fancy yellow diamond, and it's got some inclusions in it here. It's got a few of them that look, they look colorless. They could be pale yellow. It's hard to tell here, but we're going to use Raman spectroscopy to try to identify them. And you can kind of think about this, as I mentioned before, as almost as though the sort of material in this inclusion has some kind of vibration to it, like it's made up of little atoms connected by springs. And sometimes I like to think about this like a tuning fork. A tuning fork, when you hit it, it vibrates with a specific frequency or pitch. So this tuning fork vibrates at 440 hertz. Well, this crystal does a similar thing when it interacts with light, particularly infrared light, but it can also give you some vibrational information with visible light. And the idea is that some energy is going to be absorbed or given off, and that amount of energy corresponds to vibrations in the crystal lattice or vibrations in the covalent bonds. So these vibrations give you direct information about the bonding environment and crystal lattice that in turn lets you identify this material. So this is what it actually looks like in practice. So here's our sample again, and we've got these inclusions in it, and we put it into this device. On the left, you can see something that looks kind of familiar. This is a microscope here, and we can aim the crosshairs of the microscope on one of these inclusions, and then it's got this whole thing on the right here that houses a lot of optics or a whole bunch of devices to redirect a laser beam that comes in here. So we've got a green laser coming into this device. It's being redirected down. It's going to hit our sample. And what we're interested in is the light that comes back, that bounces off of this inclusion. And that light will pass into this region here where there's a diffraction grating, and that light will be split out into its spectrum. And we're interested in seeing light that has been changed, shifted from that original green color of the laser. And this will give us a spectrum. The spectrum corresponds to things that are vibrating in this inclusion. So the Raman spectrum that we see for this material looks like this. So on the bottom here, this is Raman shift. This is sort of the energy shift of the light that's returning. So shifted away from that green laser beam, and it's been shifted in specific ways. So we see peaks here that correspond to different vibrational modes within this material. And based on the position and intensity of these peaks, we can identify this material. So this material is actually olivine. So again, we've got olivine. I've shown you 3 times olivine now. And the reason for this is that if we think about where diamonds are forming in this diamond window region down here, we actually have a lot of olivine. The rocks down here, a lot of them are peridotite, and peridotite is dominated by olivine. Now, this is a complicated kind of looking diagram, but remember, this is where diamonds are forming in this region here. And I want you to remember 2 things. There are sort of 2 major rocks that we find here, and they're the host rocks for diamonds. One is peridotite, and the other is eclogite. And a lot of the inclusions that we see in diamonds directly reflect these host rocks. So they're actually minerals from these host rocks. Olivine is a very common mineral in peridotites. So if we take something like garnets, for instance, we have garnets in both peridotite and eclogite, but those garnets look a little bit different. And sometimes we see garnets trapped inside diamonds, and their color actually corresponds to either peridotite often or eclogite. And in peridotite, these garnets tend to be a bit more purple or pink colors. These are rich in chrome. These are chrome-rich pyropes. And in eclogite, those garnets are a different composition, and usually they're more reddish or orange in color. So when we have an inclusion like this, we can see that it's kind of reddish. It might be hard to tell here, but it's kind of a purplish reddish color. So this is probably a garnet from peridotite. And in fact, if we look at all of the different inclusions that we've observed and list them out, we can see, we can kind of break them down into different host rock types. So here's a not exhaustive, but pretty big a listing of many, many different kinds of inclusions found in diamonds. And this is kind of a cheat sheet for us because we know we don't find anything in diamonds. We find, minerals that occur deep in the mantle, most often from peridotites and eclogites. And over here on the right, we've got another rock type that's a lot less commonly observed in diamonds. So we won't talk about that. We've also got another column here for uncertain host rock paragenesis. And I'll just point out graphite here. So graphite is a very common thing we find in diamonds, but it's not necessarily indicative of a peridotite or eclogite or some other host rock. It's just carbon. So we don't associate it with anything in particular, but it's very common to find graphite in diamonds. So let's just focus our energy here on the two most common rock types, and within those, the most common inclusions that we observe. So just these regions that are marked common here, and I've broken them out into a simplified table. So this table shows you the most common inclusions in the most common kinds of diamonds. And I've listed these inclusions out here along with the color they usually appear as. So you can see we've got that garnet that I showed you earlier. There was this purplish, pinkish, reddish color. That's a chrome-rich pyrope from a peridotitic host rock. So there are a whole bunch of different things here, but it's a manageable size list. There's only about 9 or 10 different things you need to really worry about. And if you observe an inclusion in a diamond under the microscope, sometimes you can guess what kind of mineral it is by referring to this sort of shorthand list of the most common things that we observe. For instance, if you see an inclusion that's green, well, there aren't too many things that are green. We've got 2 options listed here. One is chrome diopside, and it's usually a vibrant green color. And the other thing is clinopyroxene, omphacitic clinopyroxene. And it can be green or it can be very, very pale green, almost colorless in some cases, especially it's very thin. But we've only got 2 real good options if something is green. So that gives us a way to simplify it, at least if we want to make a guess as to the identity of any given mineral inclusion. And down here, I've also listed graphite. Don't forget about graphite. It shows up a lot. A lot of the black, sort of ragged looking material we see in diamonds is actually graphite, and it's made of carbon. So let's look at some more of these examples. So here's, we saw a chrome pyrope garnet earlier, but here's another example of one. And you'll notice something kind of interesting about this. So the actual outline of the inclusion is bigger than the color that we see. We see a little spot of this purplish color right here, but the outline of the inclusion is actually all the way over here. And there's a region in between where the inclusion just kind of looks silvery. It's almost like someone painted it with silver or put mirrors on the side. And this is actually a very common phenomenon that we see in inclusions in diamonds. Here's another example that you can see it even more clearly. This is an orange garnet. So this is a garnet that's probably from an eclogitic host rock. And this orange garnet, you can only really see the orange color in the middle of this inclusion where we're viewing it head on. But these sides where we're viewing the inclusion at a bit of an angle, and these places, the inclusion almost looks mirror-like. It's highly reflective, and we don't see any of this color. And the reason this is happening is because there's a very big difference in the index of refraction between the garnet and the surrounding diamond. So the phenomenon we're seeing is total internal reflection. And you can explain it like this. So on the left here, I've got a bit of a cartoon. Here we are, and this is sort of in plan view, and we're looking at this inclusion. And as long as we're looking at this flat face here, we're viewing it sort of head on as opposed to on an angle, light can pass in and out of this inclusion without any problem. And we can see light from the interior of this inclusion. We can see that it's orange. But if we have light that's coming at us from an angle, we'll see that the light is actually bent by quite a bit because the index of refraction of the diamond and the inclusion is very different. And this becomes important when we start looking at some of these peripheral sides, because what happens is that the light has a tendency to bounce right off the inclusion rather than enter the inclusion and allow us to see the interior. The sides, when we view them at an angle, they behave almost like a mirror. And this isn't something that's restricted to inclusions in diamonds. We see this phenomenon of total internal reflection in nature all the time. Here's an example here of a rice leaf, and this rice leaf is penetrating down into water. And when the rice leaf is underwater and viewed at an angle, it looks silvery and reflective, the same way that this inclusion looks silvery and reflective. What's going on with this rice leaf is that it actually has a layer of gas trapped right up against that leaf. So this interface here that we're looking at is between water and gas or air trapped right up against this leaf. And that has a very strong difference in the index of refraction that's causing total internal reflection. So this leaf, although we can see it being green and luscious right up here, as soon as it's underwater and we view it at an angle, we see this mirror-like behavior and we see total internal reflection. So just keep an eye out for this and keep this in mind that sometimes when you're looking at an inclusion, it's really hard to see and appreciate its color because of this phenomenon of a total internal reflection. Another thing that we can see in this image here is the shape of the inclusion. It actually has a sort of flat faces on it. It looks like a crystal, but the morphology of this crystal isn't actually controlled by the garnet itself. It's controlled by the host diamond. And this is very common. A lot of inclusions that we see inside diamonds have a cube octahedral morphology, like these little shapes here, or sometimes even octahedral morphology. And it's kind of like a negative crystal. It's the shape of this inclusion is being controlled by the host diamond rather than the inclusion material itself. So we see remnants of octahedral or cubic faces imposed on the inclusion material. So it's very common to see inclusions with this kind of cube octahedral morphology. So let's keep moving here and look at some other examples of inclusions, especially those with bright colors like these. These are some examples of inclusions that you could probably identify just under the microscope. These ones, we've got a few examples here that are bright purple, pinkish purple or wine color. And these are pyrope garnets that are rich in chrome. And these are from a peridotite host rock. And this sort of idea becomes much more apparent when we see it neighboring an inclusion like this, a vibrant green inclusion. And this is diopside, but it has some chrome in it. And the chrome is giving it a more vibrant color. So we have a vibrant purple and a vibrant green next to each other. That's a pretty good indication that we're looking at chrome pyrope and chrome diopside, and this diamond grew in a peridotite host rock. So we've got some other examples here of other very vibrant purple pink garnets from peridotite host rocks. Now here's some more examples of this chrome diopside material. So these are green inclusions, and the green color is very pronounced, again, due to this chrome content. So in these inclusions, you could probably guess that this is chrome diopside, and this diamond grew in a peridotite host rock. Here's some examples of magnesiochromite. So this is a mineral that quite often can appear opaque, so it almost looks black. But if you have smaller inclusions or you have regions where the inclusion is thinner around the edges, sometimes you can see a reddish or brownish color from these inclusions. They can even look orange if they're a little bit thinner. Here are some examples of garnet again, but this is a different kind of garnet. It's not that vibrant purple color anymore. These garnets are more reddish to orange. These are examples of eclogitic garnet. And the composition is a little bit different, and that's why they don't have quite the same color. They have a slightly different color because they have a slightly different composition. And when you see orange inclusions like these, the sort of most logical guess is that these are garnets from an eclogitic host rock. Here's another example with some orange garnets here. And these orange garnets are occurring together with some green inclusions. And these green inclusions are actually ophiditic clinopyroxene. So this is a slightly paler green. It doesn't look quite as vibrant as the green inclusions we saw a couple slides ago. But having these together, this sort of duller green color together occurring in a diamond that also has these orange inclusions, the orange and the green together give you more confidence that what you're looking at is ophiditic clinopyroxene, an orange garnet, and this diamond grew in an eclogitic host rock. Now, these next inclusions, these are examples of something that looks a bit different. This is sulfide. So a good sulfide mineral that we're all familiar with would be fool's gold or pyrite. And these are similar. These are made of iron and sulfur, but the dominant mineral here is pyrrhotite. And sometimes these occur along with pentlandite, which is an iron nickel sulfide. And we can also have a little bit of chalcopyrite, which is a sulfide that has a little bit of copper in it. Now, just looking at these, we can see the inclusion, the middle of it is kind of metallic in luster. These are opaque, so no light passes through them. And they can usually be silvery in color. Very rarely you might notice a yellowish tinge to them. They can be a little bit brassy. But one of the common features you'll see around sulfide inclusions is this large black fracture system, sometimes called a rosette fracture, because it can make like petals of a flower-like object or something like that. So these are mostly filled with graphite, so they look black. So the idea is that after these sulfide inclusions were trapped in the diamond and the diamond made its way up to surface, these sulfide inclusions have a tendency to sort of try to expand a little bit and relax as that pressure is released. The diamond comes to surface. And when it does that, it actually pushes against the surrounding diamond and causes it to fracture a little bit as that pressure is relieved. So it's quite common to see fracture systems around sulfide inclusions, and those fractures are very obvious and very black in color. Sometimes they can have a little bit of sulfide material trapped along these fractures as well. And if we're going to try to talk about this idea of peridotite and eclogite host rocks, just finding a sulfide inclusion doesn't allow you to discern between those two options unless you get some idea of the composition, because the sulfide inclusions that we find in peridotite host rocks are much more rich in nickel compared to the sulfide inclusions that we have in eclogitic host rocks. And sulfide inclusions in general are pretty common in diamonds, so these show up with some regularity. Now, here's another inclusion, and it kind of looks similar, maybe. It almost looks reflective, and it's hard to tell if this is actually metallic and highly reflective or if it's transparent and highly reflective. In this case, it actually is transparent and colorless. This is an olivine inclusion. Now, it can look like this. So this is sort of a more equant crystal shape, but sometimes they can occur in more unusual shapes. This is a sort of rod-shaped inclusion, and this again is olivine. And the reason I can identify it as olivine is because I've done Raman spectroscopy on this particular sample and identified this material as olivine. If you didn't have that information and you just saw a colorless inclusion like this, you wouldn't be able to confidently conclude exactly that it's olivine, but you could guess that it's olivine. Here's another olivine inclusion. And in this case, this one has some little fractures around it, almost like those sulfide inclusions. So these little fractures here are black, and they're black because some of the material along that little fracture has turned to graphite. So the carbon of the diamond has turned to graphite, which is also made of carbon. So it's just changed its polymorph a little bit. So this is not that unusual to find black fractures around a variety of different types of inclusions. And quite often that black that you see is graphite. And the actual mineral inclusion itself, the volumetric part of it, is the thing here in the middle, this colorless inclusion of olivine. Now, here's a really spectacularly attractive inclusion. And this is a vibrant blue color. Now, I haven't really talked about anything yet that might be blue. So what is this? Well, the most common inclusion in diamond that you would see that's blue like this is kyanite. And kyanite is used on its own sometimes as a gem material, but it can also occur as an inclusion in diamond. And it's something that we see occasionally in diamonds from eclogitic host rock. Sometimes eclogites contain kyanite as one of their constituent minerals, and that kyanite can be trapped as an inclusion in diamond. This same diamond actually contains a garnet that looks like this. We saw this garnet already, and this orange color gives us a clue that this garnet probably comes from an eclogitic host rock. And here we've got a little polished section of a piece of rock, a xenolith, that's come up from the mantle. So this isn't trapped in a diamond. This is a chunk of rock in its own right that's also been transported up in a kimberlite. And in this polished piece of rock, we can see orange garnet and this blue mineral, which is kyanite. So these are the same minerals that we saw trapped in that diamond. And again, this is part of this story of saying that these diamonds grew in this kind of host rock in the mantle. So those diamonds containing the orange garnet and blue kyanite grew in an eclogitic host rock in the mantle. And that host rock might have looked something like this. And all of this greenish gray material you can see around here, that mineral is that clinopyroxene, this omphacitic clinopyroxene. Now, here's another kind of oddball inclusion that doesn't come up that often. In the middle, we can see the actual color of these inclusions itself. So it's a group of inclusions here, and they're kind of a pale brown color. On the left and right, I'm showing a couple examples of this same group of inclusions with slightly different lighting conditions. So here they're backlit, and these inclusions kind of look like they're colorless and highly reflective. And on the right, we've got these group of inclusions, and here the light is coming from behind and not really passing into these inclusions or reflecting off of these inclusions, and they just look black. So the message here is to be very careful about your lighting environment and play with different kinds of lighting, because this is an important way to see how light reflects off of the inclusions and how light hopefully can travel through the inclusions and reveal the color of the mineral that you're trying to identify. Now, this phlogopite might have been trapped in a host rock that was peridotite or eclogitic, or it might even be some other kind of host rock. Phlogopite is not something we see very commonly in diamonds, but it does occur. And again, in this diamond, I didn't identify the phlogopite just by looking at it. I used Raman spectroscopy to help identify this material non-destructively, just under the microscope, using this laser beam system to sort of see how the material jiggles at the molecular scale. So sometimes we not just see inclusions, but we see inclusions inside inclusions. Sometimes we don't just trap a single mineral grain, but for instance, this case here, we've got an olivine inclusion. It's this colorless material around here. It's a pretty big inclusion. And then right in the middle of this olivine inclusion, we see this region of brown color. And this is actually magnesiochromite. So this little brown piece is probably a piece of magnesiochromite that existed within the olivine, and then the whole thing was trapped inside this diamond. So this doesn't happen all that often, but it does occur. And sometimes we actually have neighboring inclusions that are touching. Rather than one being inside the other, we actually have two inclusions. So you could have chromite and olivine sort of nestled together in one sort of cavity within the diamond. That also occurs, and we call those touching inclusions. And if they weren't touching, then they would be totally isolated and separated from one another. Here's an oddball inclusion. So this is one that you wouldn't really think is that unusual if it weren't for the fact that it has this kind of hazy looking brown glow to it. So this inclusion here, this sort of yellowish or brownish inclusion, has some kind of brown rim or halo. And we recognize this as radiation damage. Quite often, diamonds from alluvial settings where they've been washed up against sediments. Those diamonds can have radiation damage. We see little spots on the surface of the diamond that could be brown or green, and that's due to radiation damage of the external skin of the diamond. But in this case, it's very unusual because we have radiation damage, this brown haze kind of feature inside a diamond surrounding this inclusion. And it gives us a hint that this inclusion probably has some kind of radioactive atoms in it, has some kind of radioactive product that's causing radiation damage in the surrounding diamond. And I did Raman spectroscopy on this particular mineral inclusion and found that it is a very rare kind of inclusion in diamond. It's called monazite. And the most common kind of monazite is cerium-rich monazite. It's like a cerium phosphate mineral. But it's also possible to have these other elements substituting in there. And one of the elements that can substitute into this crystal is thorium, and thorium can be radioactive. So in this case, it's probably the thorium content of this monazite crystal that's causing this radiation halo, this damaged halo around this inclusion. And here you can see the Raman spectrum corresponding to monazite. This is how we were able to identify what mineral this actually is. Now, so far we've just been talking about diamonds from the lithosphere, from the cratonic sort of keel, that thickest, oldest part of continent where it's maybe 150 to 200 kilometers deep. But there are occasionally diamonds that come from deeper down in the earth, and we call those sublithospheric minerals, sublithospheric diamonds, or super deep diamonds. And what kinds of mineral inclusions do we see in those diamonds? Well, the story in a way extends from what we see in these shallower diamonds. So we were talking about peridotite and eclogite as being sort of the dominant host rocks for diamonds. And on the vertical scale here, we've got depth. So this is 200 kilometers deep. So a lot of diamonds that we've been looking at so far have minerals like these. They have olivine, garnets, chrome diopsides, or enstatite if they're in a peridotite bulk composition, or we could have these orange garnets or ophiditic clinopyroxene if the host rock is an eclogite. And if we were to take these rock types and bring them down deeper into the earth, 300, 400, 500 kilometers or deeper, the effect of pressure and temperature on these rocks means that some minerals become unstable and new minerals form. So for instance, olivine doesn't exist anymore if you take it down deeper than 400 or 500 kilometers, and the crystal structure changes. So we see changes to the mineralogy of both of these kinds of rocks. And sometimes we see these new minerals appearing in diamonds. So things like majoritic garnet, garnet that has more silica in it than it really should because of the effect of pressure. And when we find these high pressure minerals, we know that this diamond must have come from a deeper environment. So sometimes we've even found diamonds that look like they come from the lower mantle below about 660 kilometers depth. And some of these diamonds contain pairs of something called ferropericlase, which is a magnesium iron oxide, together with a magnesium silicate called bridgmanite. And this, we think, is good evidence to say that this diamond must have come from the lower mantle and couldn't have come from shallower depths. Now, I'm not going to go into detail here, but I just want to show you one example of what this ferropericlase mineral looks like, because I think, and a lot of other people would agree with me, that this is one of the most beautiful inclusions in diamonds. And this is actually the inclusion I showed you earlier, this vibrantly colored sort of purple, green, blue inclusion in this diamond. And the color that we see is actually iridescent color. So it's just a sort of an effect of light interfering with something we don't fully understand at the surface of this mineral inclusion. And if you change the angle of your viewing or the angle of the light on this specimen, you see different colors appearing. So I've got a picture here of the same inclusion viewed from a slightly different angle, and it looks a totally different color. It's almost like a peacock kind of color inclusion. And we see a similar phenomenon to this in oil slicks on puddles or in soap bubbles. It's an interference kind of color. So it's caused by white light interfering with itself, and some colors are constructively interfered and they appear as vibrant colors, while other colors are destructively interfered and those colors are not pronounced. So this is something that we see in soap bubbles or in oil slicks, or even in fractures. For instance, you might have seen this in quartz. Quartz often has very thin fractures in it that have this same kind of iridescent appearance, again, due to thin film interference. So the white light is interacting with this tiny, tiny air gap where this fracture enters this piece of quartz. And we see a whole bunch of colors in here, the same kinds of colors we would see in a soap bubble or an oil slick. And these are the same kinds of rainbow colors we see in ferropericlase inclusions. Here's one more example of a ferropericlase inclusion with this sort of peacock play of colors. But if we view this same inclusion at a slightly different angle and get the lighting just right, we can see the interior of this inclusion, and the interior is actually brown. So the mineral itself is more of a brown color, and this beautiful color that we see is just an effect at the surface of that inclusion. And I'll show you one more example of ferropericlase, and that's here. So I showed you this diamond earlier. It's this fancy blue diamond with these black inclusions in it, and these are actually ferropericlase. And this stuff I identified using X-ray diffraction. So you can actually aim the X-ray beam at an individual inclusion and identify it as ferropericlase. I actually have electron microprobe data to go along with this, so we know the exact chemical composition of this ferropericlase. And when we combine that with the X-ray diffraction data, we can tell that the crystal structure of these inclusions is really squeezed. It's being compressed by the surrounding diamond. These inclusions are actually under a tremendous amount of pressure right now, even in this picture. These inclusions are under about 1.8 gigapascals of pressure. And the only way you can really explain this tremendous residual pressure is if this diamond came from a very deep setting in the mantle. We can actually say that based on that inclusion pressure alone, this diamond must have come from a depth greater than about 300 or 400 kilometers. So immediately, this diamond is a super deep diamond. It comes from somewhere below that continental lithospheric keel. And this is among this rare group of diamonds that come from these tremendous depths, reaching even as deep as the uppermost lower mantle. So it's possible that this diamond might have even come from below 660 kilometers deep. And you wouldn't know this if it weren't for the fact that it has these inclusions that you can appreciate and study. Now, I've showed you some of my own inclusion pictures here, but if you'd like to see more examples of inclusion pictures, I would direct you to these two books here. They have lots of great pictures of inclusions in diamonds with some explanations of what these inclusions are. One is The Micro World of Diamonds, and the other is Diamonds in Nature. So both of these diamond books have lots of great pictures of inclusions that if you want to see more images to compare with, maybe to compare with your own diamonds, I would direct you here for some more helpful images. So what I've shown you, hopefully, is that inclusions can be identified, and you could take a few angles of attack here, trying to understand what they're made of, their composition, what the crystal structure is, maybe using X-ray diffraction, using other spectroscopic features like how the bonds jiggle using Raman spectroscopy, and also the visual appearance of inclusions can be very helpful. So their color, their luster, their shape and texture, or if they have any iridescent colors like this ferropericlase inclusion. And I'll just list this sort of cheat sheet here again of sort of the most common inclusions in the most common kinds of diamonds, along with their typical colors here. So these are probably the most common things you're going to encounter if you have inclusions in a diamond. And don't forget about graphite. It's probably one of the most common things. And also sulfides that you see both in peridotite and eclogitic host rocks. So I hope you can see that inclusions, especially if you get the chance to view them up close under a microscope, they're actually quite beautiful sometimes. And beyond that, inclusions have a tremendous scientific value for researchers like myself as a sort of record of the geological processes occurring at extreme depths inside our planet, information that we could access in no other way. So thank you, and I can take any questions you might have.
All right, Evan, or Dr. Smith, thank you so much. That was such a great presentation. I know I learned a lot, and we've gotten tons of questions. So we will take questions for the next 10 minutes and encourage you all to submit them as you can. All right, Dr. Smith, let's start off with the first one. We had a question about chrome dioxide. I had thought chrome dioxide is only mined in Siberia. Can inclusions of chrome dioxide within diamonds be found elsewhere, though?
Yes, I mean, virtually any diamond mine where they're recovering peridotitic diamonds will have some diamonds that have chrome dioxide inclusions in them. But I think the caveat here is that the chrome dioxide that you find as inclusions within diamonds is very, very small. So most of it is smaller than the width of a human hair, and none of this material is going to be used as a gemstone in its own right. So you don't have pieces of gem quality chrome dioxide that are sourced from a diamond. The chrome dioxide that we see inside diamonds is sort of an oddity as inclusions, not as something that's going to be used as a gem material.
Awesome. All righty. Can you tell us a little bit about sapphire and ruby inclusions in diamonds? Are those common? Do you see those often? We've had a few questions about that.
Yeah, I guess people latch onto that idea because rubies and sapphires are spectacular gemstones in their own right, and they do sometimes occur as inclusions inside diamonds. They're pretty rare though. So when we're talking about ruby and sapphire, the mineral we're talking about is corundum, an aluminum oxide. And this is something that you can have as an accessory mineral inside usually eclogite. So eclogite is this one major host rock for diamonds, and sometimes it can contain mineral grains of corundum, and sometimes that corundum can be trapped inside diamonds, and you can have an inclusion of corundum, but it's very rare.
Great. So can you tell us a little bit about the difference between maybe examining inclusions in rough specimens and cut stones?
Yeah, so I love examining rough diamonds whenever I can, and the advantage with rough diamonds is that nothing has been cut away or polished away yet. So when you're examining rough diamonds, you have the maximum preservation of inclusions. So if there are inclusions in a given diamond, you're going to see them in the rough. The drawback of looking at diamonds in the rough is that the surface of the diamond is very irregular, and sometimes it can even be frosted. So it's very difficult to see the inclusions in it. And if you wanted to examine them, for instance, under the microscope or use Raman spectroscopy, if you can't see the inclusions, you really can't study them very effectively. So then you're limited to a sort of more expensive or time-consuming techniques like X-ray diffraction, and you would be doing it blind, trying to sort of bounce an X-ray beam into this diamond and examine whatever inclusions are present. So in that respect, there is an advantage to looking at cut and polished gem diamonds, where you have the maximum possible chance of seeing everything that's inside that stone, and you can look at it from multiple different angles. The drawback is that some of the inclusions may have been completely removed, and the resulting diamond could be totally flawless, and you have none of that inclusion information left anymore.
Great answer. So this is a question I've been wondering about as well. Can inclusions be affected by the journey of a diamond to the surface? You know, for example, can a inclusion become something else as heat and pressure changes as the diamond comes closer to the surface?
Yeah, absolutely. Let me just pull up a slide here. I have a bonus slide here. this one. Okay, so these are some examples of inclusions from super deep diamonds. So these inclusions might have been trapped at 500 or 600 kilometers deep, and they have really changed a lot on their way to surface. Especially if you look at this one on the left here, this used to be one mineral, but as it came up to surface, it has sort of unmixed into 2 or 3 different minerals. And you can actually see a colorless region and a sort of black region here. And it's unmixed almost the way that oil and vinegar salad dressing might unmix. So this unmixing has happened because the diamond has been taken from this tremendously hot and pressurized region deep in the earth and brought up to surface. So you've removed a lot of this confining pressure on the diamond, and some of the mineral inclusions in it will change to other minerals because you've removed that pressure. The other thing that can happen that you see around some of these inclusions is that they've ruptured the surrounding diamond. Some of these almost look like they've exploded. And again, this is an effect of removing that confining pressure. So yes, diamond inclusions, they can change tremendously during this journey to surface, and the inclusions we see might be a totally different mineral now, and we have to backtrack what we think the original mineral inclusion might have been.
All right, we got a couple more. Can you tell us a little bit about graphite inclusions? Are these from the environment the diamond forms, or is this a result of a change in the diamond crystal structure? We've had quite a few questions about this, and I think it's important to talk about.
Yeah, it is. So it's possible to have graphite forming at the same time as diamond. You can have metastable graphite forming at the same time as diamond, and that metastable graphite can be trapped in the diamond. Now, this might not be particularly common. I haven't seen very many inclusions that look like a nice crystal of graphite that's been surrounded by diamond. Much more common than that is graphite in diamonds where the graphite has resulted from diamond that has depressurized and changed to graphite. And for instance, even in these inclusion images we see here, this big black region that you see, and you see this black material around this inclusion here, all of this is graphite, and it's been turned from diamond to graphite because locally around that inclusion, the pressure has dropped a little bit, and you've allowed some of this carbon that's in the diamond crystal structure to change to carbon that's in the graphite crystal structure. So you can sort of have both of these scenarios where you have pre-existing graphite at mantle depths that's trapped in the diamond, or graphite that forms sort of in the diamond after the diamond has grown, maybe on its way up to surface inside some kind of fracture or around some inclusion system.
All right, so we've got another great question. Talking about mineral inclusions, how much of an effect from the color of the mineral inclusion in a diamond do you see on the color of the diamond?
Yeah, the answer is usually not much. Usually the color of the inclusions doesn't impart much color at all to the color of the whole diamond itself. I would say a rare exception is when we have very large inclusions, or particularly where we have inclusions that have a big fracture on them, and that fracture reaches the surface of the diamond, and then you allow sort of alteration near the Earth's surface, alteration of minerals causing iron oxide to form. So we can have some fractures or feathers that are filled with this reddish staining, this iron oxide staining. And when you have that happening in a diamond, that iron oxide staining can kind of give the whole diamond a reddish brownish appearance. So that kind of an inclusion can impart a significant color to the diamond. But for the most part, the mineral inclusions, actual crystals that are trapped inside the diamond, don't tend to give the diamond much of a color at all.
Good to know. We had one question about that quartz that you showed earlier with the iridescence.
Yeah.
Can you tell us a little bit more what's going on with the iridescence, and then we'll probably have to wrap up this talk for today.
Why don't I just go back to that slide and make it easier? So in that piece of quartz, there is a fracture in it. So there's a crack. and that crack has some width to it. It might be, 1 or 2 microns, just a little tiny, tiny gap that's actually filled with air. And now when light passes into that quartz crystal and interacts with that little gap of air, this little tiny fracture filled with air, it will bounce in between this sort of layer and cause something called interference. So the white light is sort of constructively and destructively interfered to cause some colors in that white light to pop out and other colors in that white light to disappear. And it's the same kind of phenomenon we see in soap bubbles. When you look at a soap bubble very carefully, or a slick of oil on a puddle, we see these rainbow colors that are kind of flowing all over the place. And these colors are because there's a very thin layer of this film on top of that puddle, or this thin layer of soap bubble. And it can do the same thing where light enters that layer and undergoes constructive and destructive interference that causes some colors to be constructively interfered and we see them, and other colors are destructively interfered and we don't see them. So it's the same phenomenon that we see in soap bubbles, and we see it in inclusions like these as well. It's called interference colors.
All right. Well, to everyone who joined us today, thank you. And thank you to Dr. Evan Smith for a brilliant presentation. I know I learned a lot as well. For those of you who have more questions, feel free to reach out to us on our social media platforms on Twitter, LinkedIn, Instagram, and Facebook. And please don't forget to join us in 2 weeks. We have another presentation titled Sapphires from Ceylon to Ethiopia with Wim Vertriest from our field gemology department. And I can tell you it's going to be a fantastic presentation just like today. And we hope to see you in a few weeks. Thank you so much.
Thank you.